Welcome. This is 49F5 and this is the best practice for creating closed Gaussian surface. So here's the deal. We want to work out the electric field at a certain point relative to other charges, and we need to do this by we make a Gaussian surface. It's the potato shape I showed you before. We might have some charges here, and then I can draw a Gaussian surface. Now, the problem with a Gaussian surface like that is that it's really hard mathematically, because every little window has a different area vector, electric field, vector angle, and different distances from the charges. So in this case, it would be really hard to work out anything based on Gauss's law, even though Gauss's law is correct and it applies for the entire Gaussian surface. So clearly, the more I can simplify the relationships, the better. And so some Gaussian surfaces make life easy, and some Gaussian surfaces make life hard. And so there are some patterns for designing a Gaussian surface to make life easy. And if we learn those, life gets easier for us. So if we look at the Gauss's law, we see that, my flux is equal to the integral of E dot dA, which equals my Q inside over epsilon naught. And it's this middle bit that's kind of important at the moment, because we want to manipulate that. And what we find out is that if we pick Gaussian surfaces that have certain characteristics, and there's four, I think, that I point out here. The first is if we can pick out a Gaussian surface where the electric field is constant over the surface. Well, we can get that by having things be equal distance from a point source of charge. That would be nice. So we look for something like that. That's a good aspect. Second thing we might look for is if the dot product can be expressed as a simple algebraic product, because the electric field and the area vector are parallel. So for instance, in this example here, because I'm using a symmetrical spherical surface, then at all points the electric field is radial as it cuts through the Gaussian surface, and the area vector is radial. So we find that these two vectors are parallel, and so the angle between them is 0. And so when we expand, E dotted with dA is equal to the magnitude of E times the magnitude of dA times the cosine of the angle between them. Because this angle between them is 0, and cosine of 0 equals 1. So this simplifies into E dA. That's a really good thing to find. Alternatively, if you can't find that property, then let's go to the other extreme and say if the dot product is 0 because E and dA are perpendicular. That's a good example, a good alternative. You don't want something where this angle is neither 90 nor 0, because then you've got to do some additional evaluation. Then the final thing is if you could find a region where the electric field can be argued to be 0. So you don't have to worry about it because the electric field is 0. So we're looking for these symmetries. And yes, for the point charge, and for the ball of charge, and for the shell of charge, we'll basically be working with Gaussian surfaces that are spherically symmetrical about the center of the charge. Maybe they're inside, maybe they're outside, but they'll be spherically symmetrical. But for example, if I have a line of charge, then a sphere won't work. And for something like that, I'd probably prefer to use, in fact, I know I'd prefer to use a cylinder, and so on. Now, in fairness, the people who developed this work were very inventive and very creative, and etc. We're coming along afterwards, and there's certain classical examples that we look at, and your job is not really to invent Gaussian surfaces. It's really at this stage, it's to remember which ones are used and why. It's the appreciation of what people did before us, as opposed to our own invention. So let's look at these questions. So true or false? In performing Gauss's law calculations, you should draw a Gaussian surface that has a constant or zero electric field. And that's a good thing to do. So I would say that's true. Yeah, if you can do that, that's great. True or false? In performing Gauss's law calculations, you should draw a Gaussian surface that has E and dA parallel, or E and dA are perpendicular. And that's also a really good thing to do. And then true or false? In performing Gauss's law calculations on a Gaussian surface that has E perpendicular to dA, the electric flux through the surface is zero. And yes, flux is equal to the integral of E dotted with dA, those are both vectors of course, which equals Q inside over epsilon naught. And in this case we say that E is perpendicular to dA. Well, let's expand this. This is the integral of E magnitude dA magnitude cosine the angle between. That's what a dot product is. And if E is perpendicular to dA, that means that this is the cosine of 90, which is 0. So that goes to 0, which means that my flux goes to 0. And so that is a true statement. Cool. There we have it.